Hey everyone, welcome back. We're going to be doing more calculus today, and this is our second look at the L'Hopital's rule. And this gets a little bit on the mathy side. There's, maybe one or two things, especially if you're not comfortable with natural logs and exponentiation. So let's go ahead and get started with it. So we have this Indiana Jones and the Temple of Doom. We've got after crash landing in 1935 India, a local village implores Indiana Jones to liberate the Pankot Palace from the Thuggee cult and return the sacred stone. After arriving at the palace, Jones is treated to a banquet with Maharaja of Pankot, Zalim Singh, and Prime Minister Chatar Lal. The food served is adventurous for Jones, a snake surprise, beetle's eyeball soup, and chilled monkey brains for dessert. Now, probably not the most PC thing here out there, but that was the 80s, I guess. In the spirit of adventuresome cuisine, let's take a look at some adventurous limits. All right, adventurous limits. So here are three indeterminate forms which are not indeterminate forms in the classic sense. All of these don't really make sense kind of mathematically. We've got 1 to the infinite power, which, you know, seems like it'd just be 1 because you're multiplying 1 over and over again. But is it really just equal to 1? We have 0 to the 0 power, which conventional wisdom, 0 times anything, including 0 times 0, is equal to 0. However, we have 0 to the 0 power, and also anything to the 0 power is supposed to equal 1. So is this 0 or is this 1 or is this neither? Also, we have infinity to the 0 power, which seems weird because we have, well, first of all, infinity isn't a number, and we're taking it to the 0 power. So, the best we can say is a really large number to the 0 power. Should that be 0? Should that be 1? It's really kind of hard to say. So this is kind of weird math because we're taking things that, I don't know, I don't want to say it's objective or subjective, but it really depends. I think this is the best way to say this. So these limits really depend on how you get there. So first of all, we're going to need this concept where if we have the function of f is equal to a limit, then if we exponentiate the limit of the explanation, e to the f, is equal to the exponentiation of the limit, e to the l. So we can exponentiate both sides and preserve the limit. So the strategy that we're going to use for these weird indeterminate forms over here, the strategy that we're going to use is to, first of all, create a limit for the natural log of f of x. Usually you're going to see me write the natural log of y. We're going to create an indeterminate form and use L'Hopital's rule to evaluate that limit. And this is kind of the classic indeterminate form, 0 over 0 or infinity over infinity. And then we're done. We're going to use our brand spanking new concept here, and we're going to exponentiate on both sides to find a limit for f of x. So let's start off with this one over here. We've got the limit of x to the x power as x goes to 0. Okay, well, what form is this? If we try direct substitution, we get 0 to the 0 power, which is one of those three strange indeterminate forms. So we're going to try the technique that we just learned, kind of learned, didn't really learn, but we're going to try that technique with this limit. So first of all, we're going to say the function y is equal to x to the x power. Now, because a natural log is going to simplify the right side, we're going to take a natural log of both sides. So the natural log of y is equal to the natural log of x to the x power. All right, sounds pretty straightforward. The next thing is we're going to use powers of logs. So we have the natural log of a to the b power is b multiplied by the natural log of a. In our case, our exponent is x. So we're going to front multiply by x, and we're going to keep natural log of that same base, x. Now that we have that, we're going to take this x and we're going to turn that into 1 over x on the denominator to kind of create algebraically indeterminate form. Our numerator is going to stay the same, natural log of x. And so when we're done, what we're really saying is the natural log of y is equal to the limit of y, the limit of the natural log of y is the same thing as the limit of the natural log of x divided by 1 over x, which is good because this limit we can use L'Hopital's rule for. So let's try to use L'Hopital's rule. Always check if you have an indeterminate form. So if we try to directly substitute 0, we get the natural log of 0, which is negative infinity, and we get 1 over 0, which approaches infinity. So that's infinity over infinity, technically negative infinity over positive infinity, but that doesn't really matter as long as it's an infinite form over an infinite form. We can use our L'Hopital's rule. So we're going to use L'Hopital's rule. The derivative of natural log of y is 1 over x. I'm sorry. The derivative of natural log x is 1 over x. And the derivative of 1 over x is negative 1 over x squared. After doing this for a while, you kind of get the derivative of 1 over x in your back pocket. And you can just bust it out whenever you need to. Okay, we're going to use L'Hopital's rule now. And this becomes the limit as x approaches 0 from the right of, oh, we did use L'Hopital's rule. What am I saying? We're going to simplify this, and we get the limit as x approaches 0 from the right of negative x. There's nothing wrong with this limit. Now we can just directly substitute, and we get 0. So this tells us that the limit of the natural log of y is equal to 0. Therefore, the limit of y is equal to e to the 0, which equals 1. And if you remember what y was x to the x power. So this says that the limit as x approaches 0 from the right of x to the x power is equal to 1. So 3 things here. Check for indeterminate form. Evaluate the limit of the natural log, and then exponentiate to create the limit of the function. Here's our important ideas. We've got our 3 advanced cases of indeterminate form. We're going to find the limit of the natural log, use L'Hopital's rule, and then exponentiate. So with those 2, 3, depending on how you number them, that should get you through any of these weird advanced cases of an indeterminate form. So we got 2 examples to try. The first one is the limit as x approaches 1 of x to the 1 over x minus 1. Let's try direct substitution. If we directly substitute, we get 1 to the 1 over 0, so 1 to the infinite power, which is an advanced indeterminate form. So we're going to say that y equals x to the 1 over x minus 1 power. The natural log of y is equal to the 1 over x minus 1 multiplied by the natural log of x. Kind of combined 2 things here. Maybe I should slow that down for you. It's equal to the natural log of x to the 1 over x minus 1 power, which in turn is equal to 1 over x minus 1 multiplied by the natural log of x. Now we're going to apply a limit to both sides. So the limit as x approaches 1, that's what it says here, of the natural log y equals the limit as x approaches 1 of 1 over x minus 1 multiplied by the natural log of x, which, by the way, simplifies into the limit as x approaches 1 of the natural log of x, all divided by x minus 1. Let's do an indeterminate form check again. If I substitute 1, I get the natural log of 1, which is 0, and I get 1 minus 1, which is also 0. So now we have an opportunity to use L'Hopital's rule. The limit as x approaches 1. Now the derivative of natural log of x we know is 1 over x. The derivative of x minus 1 is 1. And now we can directly substitute into this to get 1. Put together, that just told me that the limit as x approaches infinity of the natural log of x to the 1 over x minus 1, that's equal to 1. And then here's where that exponentiation comes in. This can be further deduced from, or from this we can deduce that x to the 1 over x minus 1, that limit is equal to e to the first power. And I think I'm getting this wrong. This limit's going to 1. Right. So the limit is e. 1 to the infinite power is equal to e this time. Next time this might be different. Let's try the second one, and let's see if this turns into an indeterminate form. If I substitute 0, the base becomes 1 over 0, which approaches infinity, and the power becomes, well, you can directly substitute 0. Infinity to the 0 power is an indeterminate form in disguise. So we'll set up what we know, or what we started off with. Sorry, we'll set up with our plan, which is start by saying that y equals 1 over x cubed to the x power. Next, natural log on both sides. So the natural log of y is equal to the natural log of 1 over x cubed to the x power, which simplifies to x natural log 1 over x cubed. Okay, apply a limit to both sides, the same limit. The limit as x approaches 0 of the natural log of y is equal to the limit as x approaches 0 of x natural log 1 over x cubed. Let's turn this into an indeterminate form, or what we think might be an indeterminate form, using the reciprocal of one of those factors. So natural log of 1 over x cubed over 1 over x. Try direct substitution. We have the limit, or the natural log of 1 over 0, the natural log of 1 over 0. 1 over 0 approaches infinity. Natural log of infinity goes to infinity. And 1 over x, as x goes to 0, that also approaches infinity. So this is infinity on infinity, which is a classic indeterminate form. So we use L'Hopital's rule to evaluate. And we've got the limit as x approaches 0. Now the derivative of the natural log of 1 over x cubed, stick with me, this is 1 over x cubed multiplied by the derivative of 1 over x cubed, which happens to be negative 3 over x to the 4th power. Now on the denominator, we have 1 over x, and the derivative of 1 over x is negative 1 over x squared. Now we've got a lot of exponents to clean up here, but when we do, well, this kind of simplifies to negative 3x cubed over x to the fourth over negative 1 over x squared, which further simplifies to 3x cubed over 3x squared, which ultimately simplifies to the limit as x approaches 0 of 3x, which we know is 0. So what have we shown? We have shown that the limit as x approaches 0 of the natural log of y equals 0. So this means the limit as x approaches 0 of y equals e to the 0, which is 1. And then when we substitute back for the natural log of y, when we substitute back for y, we get the limit as x approaches 0 of, well, what was y? Y was 1 over x cubed to the x power. That's equal to 1. So that's all we've got for you today. It's going to take a little bit of practice to get this done. These exponentiation problems can run a bit long. So good luck to you, and we'll see you next time here on AP Calculus.